All right, let me share my screen real quick. I hope folks can see the screen?
We see it. Thanks,
Okay,
Ahmad.
cool. So hi everyone, my name is Ahmad, and I'm going to be doing a short presentation on CUDA and C++ and basically doing a case study in how to optimize code, C++ code in CUDA. So let me just give a brief introduction about myself. My name is Ahmad Sharif. I'm a C++ and CUDA user. I'm a bit of a performance enthusiast. I like digging into details, going to low-level stuff, trying to understand how the machine is working and try to utilize more of it. I like debugging and fixing slowness, and that's sort of what I'm doing currently at Meta. I work on performance. I'm actually not representing Meta today. Like this is just a kind of a personal talk. So yeah, that's it. With that caveat, let's dive in. So this is the agenda for today. I'll be talking about the CUDA programming model, and I'm actually kind of curious. I hope people in this meeting know a little bit about CUDA because I'm gonna go over some of the intermediate and advanced topics. I'll also talk about the H100 architecture, and I'll actually demo if I have the time to actually run the kernels and see how like the performance is for various kernels. And we'll be doing the case study of simple matrix multiplication, and I'll tell you why I chose matrix multiplication in a little bit. So this is the CUDA programming model. I directly stole this slide from NVIDIA's documents. Basically, the GPU is a massively multi-threaded machine, and the basic building block is a single thread. You have groups of threads that can access that are called what is called a thread block, and they can access shared memory for synchronization or doing collective work together. And then you have something called a thread block cluster, which the GPU guarantees that you will schedule and concurrently run these blocks at the same time. And they can also do some synchronization and coordination amongst themselves to do a bigger piece of work. Um, and then you have a grid with multiple thread block clusters all accessing global memory. And you can also use global memory to synchronize across the entire kernel, but typically that's very slow. Now I'm going to talk just a little bit about how those threads are actually run on, let's say Hopper. Hopper is uh, one of the newer GPUs that NVIDIA has. I think now they have Blackwell and like Vera Rubin is going to come out. Hopper has like 50 megabytes of L2 cache, and it has approximately 132 SMs. Typically, the number of SMs can actually vary too based on the yield of the wafer of the chip. Like if there's some defective SMs, I think they can turn them off. But basically, each SM has some tensor cores, some FP32 cores, a couple of like four schedulers, and you have a lot of them. So you have to launch the kernel that you launch, the code that you run. It executes on like you try to utilize all of the available like ALUs and hardware on the machine. Each SM looks like this. So typically for x86 64 or something, if you're used to that hardware, you may think of registers as like a limited number of registers, like maybe, I don't know, tens of registers with a XMM and other vector registers. Maybe there are like 100 registers on x86 64. But the register file for in each SM, and there are 132 of them on Hopper. It has 16,000 registers in each of the subpartitions, and there are four subpartitions within each SM. So there's 256 kilobytes of registers per SM. Then you also have a tensor, like four tensor cores in each SM, and then you have 32 FP32 units in each partition. So 32 threads, um, 32 CUDA threads form what is called a warp. And each of these four subpartitions within the SM can issue one FP32 instruction, like a floating point instruction in the same cycle. So that's a little bit about the FP32 side. There's also like in32 cores. These FP32 cores and in64 and FP64 hardware that is called CUDA cores. I don't know if you can see my mouse, but that's basically on the left side of the tensor core. And then you have like the load store units, also the special function unit that can do like sine, cosine, exponential operations and logarithm and stuff like that. And then you have the tensor core, which is actually responsible for if you want to extract the maximum performance in terms of like matrix multiplication, you have to use the tensor cores there. And so basically there's four subpartitions. Each one can issue one warp, which is 32 threads at the same time. So this is like a massively parallel machine. And there are 132 of these SMs, like I said. There's also 256 kilobyte of L1 cache, which is a slash shared memory. You can configure it. You can say like, I want to use this like as a software programmable shared memory completely, or you can say like use this as the L1 cache, which is like hardware managed. It'll pull the data into this cache before like whenever you access it automatically. If you want for typical kernels that you want to extract the maximum performance for, you use this as a shared memory yourself, which you yourself manage as a programmer. The Hopper SM also introduces this thing called a Tensor Memory Accelerator, TMA, which is basically so specialized hardware unit that can bring in data from global memory and do some bounds checking on it asynchronously. So one of the threads can just issue one instruction and it can bring in that data from global memory into shared memory, and you don't have to issue further instructions for it. So in one of the kernels, I'll actually show you how to use it, and we can see that. So here are some raw H100 numbers. The clock speed is 2 gigahertz approximately. There are 132 SMs per GPU, like I said, and each SM has four subpartitions, and each subpartition has 32 FP32 units. So if you just compute the number of flops per SM per cycle, there are 256 flops per SM per cycle. The two is because of the fused multiply add instruction. And if you compute the FP32 teraflops per GPU per second, you get about this number, which is 67 teraflops. So the Hopper can do 67 teraflops of FP32 per second. And that's not using the tensor cores. That's just using the CUDA cores. If you want to use the tensor cores, you can actually get up to 494 teraflops, just because of the way the maximum capacity of the tensor cores in terms of like what sub matrices it can actually multiply out. That's the arithmetic like hardware limit on the GPU, but I've only been able to, like, I'll show you in the following examples. I haven't been able to actually hit 494, and actually cuBLAS itself cannot hit that because I think there's probably thermal throttling that happens if you toggle that many bits on the GPU. It'll throttle the clock speed or something. Like the most I've able to hit on for this example was like 300 something teraflops, but that's still a lot of flops. Like teraflops is like one with 12 zeros. It's probably a lot more than the CPU. And the GPU itself has, like I showed you, those the SMs and the L2 cache. That's one die, and then there's a HBM die that's stacked on top of that one, and that's basically the memory of the GPU, the global memory, and then the bandwidth from the like the core to the HBM is 3.3 terabytes per second. This is again a sheet from NVIDIA that shows you all of this, like the GPU memory bandwidth, like the tensor cores. And generally speaking, the lower precision you have, like FP8 or something, you can get more teraflops. So I will be talking about matrix multiplication, and the first thing to ask is like, why am I using matrix multiplication as my benchmark? It's a very common operation for machine learning or AI workloads. Basically, any linear layer that you use in your neural network that gets in the forward pass that gets when you evaluate the weights, it gets translated into a matrix multiplication. Even the attention kernels, like part of that is matrix multiplication. And in the backward pass, also like the linear layers convert, like they are translated into two matrix multiplications, one to update the gradients and one to update the weights for the backward pass. And this is an interesting case study because if you just naively write simple code, you may not get the full machine utilization, and you may not get you may not fully saturate the machine. So you need to do a lot of tricks, and sometimes you have to do hardware specific optimizations to actually get the full performance from the hardware. So the matrix sizes that I'll be using for this case study are fairly large because I wanted to see like how much can I push the arithmetic hardware on the machine. So I'm going to be using C equals A times B. C is 4K times 8K. This is like number of rows times number of columns. Um, and A was 4K by 16K. So like M by K, M is 4K. And then B is K by M, which is 16,000 by 8,000. So if you just look at the number of bytes of A, B, and C, there are 512 megabytes for B, 256 megabytes for A, and 128 megabytes for C. So combined, they're close to like 1,000 megabytes. But if you look at the floating point operations needed to compute this matrix multiplication product, it's about approximately 1 teraflop. And roughly speaking, I chose large matrices because roughly speaking, like the bandwidth is proportional to the to like n squared, and the floating point arithmetic needed to compute the product is n cubed. So if you compute the ratio of the flops to bytes, it's very high. And this thing is called the arithmetic intensity of the workload. And it's more than 1,000 flops per byte. So the very first thing that I did was I just ran cuBLAS on it. cuBLAS is this library that NVIDIA provides that is kind of is quite optimized for their hardware, and I just wanted to run like how many teraflops can I get, and what is the duration of the kernel that I if you pass in like C equals A times B to this library that is already optimized, just to get an estimate of like what is the highest I can hope to achieve, or like can I get close to this performance or not? Because NVIDIA has an army of engineers that are trying to optimize this. So for FP32, which is like the true 32-bit float, I was able to get duration of 31 milliseconds, and the teraflops is 35. And I have two more columns here, which is one is percentage of cuBLAS FP32, which of course cuBLAS FP32 is 100% of itself. And the other column is percentage of cuBLAS TF32. So you may be asking, what is TF32? TF32 is another floating point format, which is just 19 bits. So by reducing the precision of the floating point number in the internal representation of the hardware, you can actually save a lot of area, and you can have a lot more hardware units, and you can achieve like faster multiplication if you use that at the cost of lower precision. So cuBLAS has this mode where you can say like I want TF32 or FP32. If you use TF32, you can see the duration almost like drops by 10x, and the teraflops per second goes up by almost 10x. So uh, like this line, you can multiply these two matrices in just 3.5 millisecond. And then the teraflops per second, like I said, the advertised teraflops per second for Hopper H100 is about 500 approximately, but I was able to get only 317 for it. Any questions so far? If people have questions, feel free to interrupt me. So this is again, this is what I was mentioning, FP32 versus TF32. TF32 is just like the mantissa part of the float is just 10 bits, and the exponent is exactly the same. So it's like one sign bit. So the total is 19. And Basically, it takes in 32-bit FP32, but the internal accumulate is happening in TF32. All right, so let me start with just like the simplest kernel that I can think of. Like I said, you have this GPU that can have like thousands or millions of threads. And this is an embarrassingly parallel problem. So let me just do the simple thing, which is for each element of C, I'm going to launch one CUDA thread, and this CUDA thread will do the dot product of this row and this column. So I hope everyone remembers matrix multiplication from high school. Basically, each result of C is a dot product from A and B, and you can look at the you can actually look at the sizes here. Um, Basically, the number of bytes read is this much, and what I'm doing here is each thread here is reading one entire row of A and one entire column of B. And the hardware is doing some caching in the L2, but I'm not doing anything smart here. So there you can see there's a lot of redundant reads here because the adjacent thread here, which is one thread over, it's basically using the same exact row of A, right? But it's just a different column of V. So I'm not doing anything smart here. So this is what the kernel code looks like in C++. I'm calling it matmul naive. You have ABC as float pointers here, and you're basically looping over the k dimension, which is the 16,000 elements, and you're computing this dot product here, and then you're just setting it to C. And this is how you launch it in C++ on the host side. So the way CUDA works is like you write this kernel, which I had before. This like underscore underscore global thing, this code will run on the GPU. And then you have something on the host side, which is how you launch this. And you configure what is my block of threads. So I'm using 16 by 16 block of threads here. What is my grid size? I'm basically doing like just the uh, like a tile divide of N and M such that I fully cover C. Like my C is actually divisible by 16, so it's not a problem. But generally speaking, you do this just to make sure you fully cover C. And then you just call this kernel using these three angle bracket notations with a grid and block and the pointers and the sizes, and it will launch the kernel. So this kernel is basically launched for it launches one thread for each element of C. And what are the results for this? If you look at if you run it under NCU, you'll find that the NCU is the kernel profiler for NVIDIA. You'll find that the duration here is very bad. It's like 10 times longer than the cuBLAS kernel. I'm only able to get 10% of the cuBLAS FP32 and only 1% of the TF32 teraflops. So now let's do a little bit better. This you can just like find in if you just try to find online like how do you optimize matrix multiplication. One of the first things to do is, like I said, we were overreading A and B, where we were like each thread, adjacent threads of were reading the same exact data. So instead of reading the same amount of data, that was like a lot of read amplification from HBM. What you can do is you can tile A and you can tile B, and that way, like there's a group of threads that is computing this tile of C. For this tile of C, you load this T by T submatrix from A, you load this T by T submatrix of B, and then all the threads try to reuse this thing from shared memory. So like I said in Hopper, when I gave you the architecture diagram a few slides back, you could see that it has like like each SM has shared memory, which is much faster than global memory. It's also the L1 cache, but you can program it. You can ask the hardware to like fully be like the software managed shared memory, which is a much faster memory than global memory or L2. So we bring in like all the threads cooperate to bring in a T by T submatrix of A and B, and then you compute C by going over these submatrices over and over again. You have to do this over the K dimension. But basically, if you do the math for this, you will figure out that the total bytes read compared to the naive is there's a 32x savings in theory because if the tile size is 32 by 32, actually, if the tile size T is 32, you will see that there's a 32x savings in theory. But in practice, the savings is over the naive is a little bit less because when two CUDA threads were reading the same row of A in the naive kernel, the L2 was already caching that. So we were not going to HBM all the way out. We were probably going to L2 or even L1. So the hardware was already caching stuff for us, but here we're making it more explicit. And if you if one question that you may have is like, why did I choose 32 by 32 tile here? There's a reason for it because like these two tiles, like this tile A and tile B, they have to fit in shared memory. And there's a limited amount of shared memory on the per SM. There's 256 kilobytes of shared memory in the SM, and that's why I'm using 32 by 32. And also, like if you compute the FMA to load ratio for the kernel, our kernel does there's an 8x difference in arithmetic intensity compared to the naive kernel. The naive kernel was doing like one load, and then one FMA. So the ratio between the arithmetic and loads were just 1 to 1, just 2 to 1. And then here, where when you have a large tile size, the FMA to SMEM ratio, like the amount of arithmetic that you're doing compared to the amount of loading that you're doing, that one there's an 8x difference. It became from went from 1 to 2 to 4 to 1. So this is the code for the tiled kernel, which is basically we're looping over the k dimension and we're bringing in the AS is like this underscore underscore shared is a shared memory tile from A, shared memory tile from B, and you're bringing both of them in cooperatively. So all the threads are each thread is loading its small piece from global memory to shared memory, and you need all of the tile to be available before you can do the compute. So you have to do this primitive called sync threads, which basically is like a kind of a barrier. It waits for all the threads to reach this code before moving on. So when collectively all the threads have loaded their data into the shared memory, you wait for all of them to complete, and then you just do the dot product here, and then you do sync threads again. I think there's a question. All right, I think you're unmuted.
Yes, thanks. How do we know when to make a custom CUDA kernel and when that's not necessary?
Okay, yeah, that's a good question. I don't think there's like a recipe for it, but cuBLAS gives you very high performance kernels for like elementary stuff like matrix multiplication, transposes, like things like that. So if something is available in cuBLAS, you should use that. So I just wrote these kernels just to understand the hardware, just for like educational purposes. But normally you would never do matrix, you would never write your own matrix multiplication kernel. If you're doing something like which is like a fusion of a few operators, like in machine learning, sometimes you do like a matrix multiplication followed by something like a ReLU operation or something like that. I think those kernels, if you write them by hand, you can get a lot more performance because it's better to write like one fused kernel as opposed to like two or three kernels from cuBLAS.
Thank you. Here's another question. This is somewhat general. Google has been talking about new LLM architectures involving memory, and I'm wondering to what degree can CUDA support new types of memory approaches and new types of logic embedded within LLM architecture?
Uh, I'm not sure if I understand the question. If the question is, can CUDA code run on other hardware other than NVIDIA? Uh, mm, I think other vendors are trying that approach. Like AMD can take like somewhat slightly mechanically modified CUDA code and run it on their hardware. But I think CUDA is like a NVIDIA specific thing.
Thanks. I was referring more to LLM architecture in general, new approaches. For example, uh, could CUDA have some large state machine in it that runs with each tensor operation? I mean, that's kind of a contrived example, but I'm wondering to what degree can CUDA be used like a so-called normal programming language?
uh, I think it has support for a lot of things, but uh, you could do like pointer chasing, you could do like custom things in CUDA C++. But I think there are certain limitations. For example, like the hardware doesn't support certain operations, so uh, those you cannot emulate. But maybe we can take that offline. I don't fully actually understand the question, but I think CUDA is actually an ecosystem of a few things. Like this, what I'm showing is CUDA C++. There's also like other domain-specific languages, like there's Qtile, there's a bunch of other things, and to support those languages, NVIDIA has like tools like debuggers, profilers, and stuff like that. So I think using the same C++ language, you can translate it down to other hardware. Um, I don't know if that actually answers the question or not.
Yes, thank
Yeah.
you.
Um, I think there are a few more questions. Jim?
Yeah, hi, thanks. Could you just quickly go over some of the acronyms again? SM, FMA, TMA, and then I see GEMM at the top of this file.
Yeah. So SM is streaming multiprocessor, which is like the hardware unit that actually executes these threads. Um, the FMA is fuse multiply add. That's like the term for like the doing like A like C equals A times B plus C, something like that. And the TMA was like TMA is like a hardware block within the SM that actually brings it's called tensor memory accelerator that can bring in data from global memory into the SM for SM to compute stuff on it. And GEM is generalized matrix multiplication. I think that's like just the
Uh,
library term for like linear algebra.
okay, thank you.
Yeah, Bisha.
Yeah, I kind of have two questions. One maybe with this slide, and then the second one would be um, kind of in maybe beyond the scope, but with the slide, the sync threads is kind of similar to in STD join. Is that correct?
Yeah. I actually don't know what other semantics of join is, but sync threads in CUDA, it will wait until all the threads have hit this point.
Okay, and then the second one is I know like there was an older kind of a CUDA C++ wrapper called Thrust. Is this similar to Thrust, or is this kind of a completely different uh, architecture, a different feature?
So my understanding is that Thrust was another library from NVIDIA, part of the CUDA ecosystem that exposes higher level primitives. I'm using CUDA C++ just to show the lower level stuff, but I think Cub and Thrust, I believe, are libraries from NVIDIA that expose you can do like simple things like matrix multiplication or addition or stuff like that by just calling a function there as opposed to writing the explicit code for it. That's my understanding of Thrust. I haven't looked at it in a while, so I'm not 100% sure.
Thank you.
And Vincent?
Yes, Ahmad. So there's a few things that I wanted to just briefly touch. The first is I forgot to mention that if those that have questions, they could also post in the Discord channel. I'll be monitoring it. The other thing is in regards to sync threads. I think Fisha, you just had a question on that. It's more similar to STD barrier, if that helps. Um, and then I'm going to follow up with my question, which is the difference between the FP32 and the TF32. Ahmad, can you just tell me, it seems like it's using the same hardware to do the same computation, but the format of the value is different. So one is using 19 bits, the other one is using 32. As a result, it's just taking less time. Is that how I understand it?
Actually, the reason for TF32 is one of the biggest reasons for TF32 is the tensor cores don't cannot operate on FP32. So, so if you want to use the tensor cores, you have to do TF32. And when you pass in the TF32 hint to cuBLAS, it will use the tensor cores for it because you will lose precision there. Like the results will not be numerically the same as like doing the results, doing the same operation on the CPU, which uses like IEEE format. So that's the main difference. Like if you want to use the tensor cores, or you can instruct either yourself, or if you instruct cuBLAS to use the tensor cores, you have to do TF32 or maybe like BF16 or something like that. But basically, the tensor cores don't support full 32-bit precision.
Ah, okay. Okay, thank you, Ahmad. I appreciate it.
Uh, okay, so let me move on. So um, the if you look at the matrix multiplication tiled kernel, you now see a duration drop here, and the T-flops per second is like 6.22. We're still not using the tensor cores. We're only 18% of cuBLAS FP32, and we're like 2% if you compare it with TF32, which is not a fair comparison because our code is actually numerically accurate. We're not using the tensor cores. We're just using like the regular floats here. If you were using regular floats here, like the sum is like a float. So we should be focusing on more on this column. But I just have the last column just in case, because eventually we'll start using tensor cores and will start comparing against TF30. So the next optimization that we will do is what we call register tiling. And again, this is a way to increase the arithmetic intensity of the kernel. And arithmetic intensity, as a reminder, is like the ratio of the floating point ops to the memory operations. So as a reminder, before we were taking a row of A and a column of B, and then we were just computing the dot product per thread. Now what we will do is each thread will take a column of A and a row of B, and now we can have two nested for loops, and we can actually compute the outer product, which will do the however many values we have for A and however many values of B, the product of those two in a nested for loop. We will update the value of C. This is not going to be the value of C, but this is just going to be something that we will add to the value of C to update that. And this results in basically like a higher arithmetic intensity for the tiles that we will use. For the diagram, I'm showing a 4x4 example. I was too lazy to actually do the full tile that we are using in code. But in code, we're actually, the A tile is 16 by 8 in shared memory. B tile is 8 by 16 in shared memory. Again, we can't use like too big of tiles because the shared memory is a limited resource, but we're just trying to more efficiently use shared memory. So you bring in some like slice of data or tile of data to shared memory once, and then you use it as much as possible. Like you try to fully utilize the arithmetic hardware to the maximum while you have that memory and while you have the data in shared memory. So this is the code for matmul tiled, and you like the outer product accumulation that I did not show here. I actually have a GitHub. Like if you go to my GitHub, you'll find the code for this. It is public. You will find that the outer product is doing like two nested for loops. So you cooperatively load tile A, tile B, and you do the outer product accumulation here, which is basically Tn times Tm fuse multiply adds per case step, and then you store the results there. So that basically the whole goal is to improve the compute to load ratio versus the basic tile kernel. And you see that this as a result that uses a lot more registers. The registers per thread, which is again a very limited resource on the SM, you're using more of that. You're using like 8 by 8 registers, like 64 registers here, just to store the accumulator. Forget about the index math that you're doing here. That is additional registers. So with that approach, you get a duration of 67 ms for this problem size, and you get like a 16 teraflops per second. So now you're getting 46% of kublas. So you're still like halfway there, and you're using like you get 5% of the kublas when kublas is allowed to use tensor cores with lower precision. So now we have to do some more work to get to even closer to kublas. So the next optimization we will do is we'll do matrix multiplication with vector loads. So instead of a single floating point here, what we are doing is we're reinterpreting cast it into a float 4. So the hardware can issue 128-bit loads as opposed to 32-bit loads. So the loading part is different, but everything else is kind of the same. You just have to do a little bit of casting. I'm not showing the code here because the slide gets too busy, but this is the crux of the optimization. And with that, the duration drops even further. You get like 61% of kublas here. So one other thing that I explored, which did not actually gave me optimization improvement, which I'll show you why, is in the kernel. What we're doing is we have like two phases. We load data from global memory. There's a synchronization. Then you do FMA, which is the math part, and then you do again a sync, and then you do sync like that. So the math hardware is idle for this block here, and the load hardware is idle for this block here. Although like each SM can actually have multiple blocks, so in practice it's not that idle because you have multiple copies of these kernels running on the same hardware. So there is a little bit of overlap. But what you can do is even within the kernel, you can do some pipelining here. So what you can do is you can load data into SMEM tile 1 while you're doing the arithmetic operations from SMEM tile 2. Then you can do a sync, and then you can do you can have like this circular buffer kind of a thing. It uses double the amount of SMEM, which is again, like I said, a limited resource, which can limit how many concurrent blocks you have running. But you can try to do this even within the same kernel. So this is called what I'm calling a pipe kernel. So the pipe kernel is like this. You load tile A, you load tile B, and then you compute the tile, and you like it's like a circular buffer. So you like swap current and next, and you can see 2 here, which is the shared memory stuff has to double here. So that actually, if you look at it, it actually gave me a performance reduction. And the teraflops went down from 21 to 15. And the reason for that is when I looked at the profile for this, you can see the registers per thread, it actually increased because it has to keep more things into account. So registers per thread went from 128 to 130, and that actually caused the block limit to hit. So previously there were 2 blocks that could execute on the SM at the same time, and with more blocks executing on the kernel at the same on the SM at the same time, the hardware can switch between threads, between warps rather. So it issues a load for one of the warps of one block, and then while that is being loaded, while it's waiting for the global memory, it can switch to a different thread. So the more threads you have in the system, the more latency you can hide, and that is what NVIDIA calls occupancy. It's basically how many warps are active at any given time. And you can see that the occupancy actually dropped from 15%, from like 15.5 warps per SM to 8 warps. So if there are fewer threads in the system, because GPU is like a throughput machine, you have to have a lot of outstanding threads in order to like switch to, because otherwise maybe all the warps have asked for some data from global memory and there's nothing to execute. So the math units are not going to be busy. So you have to be a little bit careful with some of these optimizations. I think Vincent, you have a question.
Yeah, so the first question I have is actually from the Discord, and I think they're asking if you could provide access to the slides from today.
Oh yeah, I can. Let me paste that actually in the Discord. Give me.
Sure.
Should I just text Rob?
Sure. Yeah, we could do it offline. Oh, they were just asking, so it seems like it could be available after the presentation, which is fine.
Yeah, actually, you can like I just made it public to anyone with a link, and feel free to like Rob can circulate that
Sure.
to Discord.
I also had another question on the previous results
On
on the pipe.
these?
On the pipe, yeah, sorry. On the pipe. So here you were saying that you're using two more registers. As a
Yeah.
result, the thread, it couldn't have so much occupancy because each thread required more registers.
Yes.
So the first question I have is on the GPU architecture, the registers themselves. Can you describe the properties? So how many registers do you currently have? Can the registers be partitioned in any way? And what are the size of the registers?
The total register file size is 256 kilobytes, and I think they are four subpartitions. Each one was, I believe, 16,000. So and they're 4 bytes. So depending on the size of the block. So previously, I think the block size is 256, which means each block is 16 by 16 threads. So if you multiply 256 with the number of registers, that one, if that exceeds the total register limit, you on the SM you cannot schedule another block. And sometimes if you even go by one over, um, then you cannot schedule it.
Okay. So each register must be at a minimum 4 bytes, you said.
Yeah, yeah.
At a minimum. Okay, so if I would use a car, it would still use, the 4 bytes to represent a car. Is that fair to say?
I believe so, yeah. I don't think you can use like single yeah, I think the minimum size to, and actually probably it rounds up to something too. So that's the granularity on the single register, but I think if you use like 135 registers or something like that, it'll probably round up to some minimum thing that it can allocate. I
Okay.
don't actually know that number off the top of my head, but I have seen that behavior.
Okay. Yeah, I was just trying to understand a little bit more of how the architecture of the register file was done. So thank you.
Yeah. So now I'm gonna look at some more optimizations. And the first one that I look at is now I want to start using the tensor cores. So the way to use tensor cores is a little bit complicated, but NVIDIA provides this library called Cutlass/Qt. If you go to GitHub, you'll find that library, and that is a nice library to handle many of the hardware details for you. So you just deal a little bit with a higher level, and then it can generate the code that uses the tensor cores, because actually it's not that easy to use tensor cores manually. You have to get the data layout exactly right and stuff like that. Cutlass also does some compile time checking to make sure the layouts and all match. So this is the code for the simplest kernel that I could come up with that does matrix multiplication using tensor cores. And you can see that this line here, this gem line, I don't know if I actually have this. This gem line is actually the one that's actually doing the tiled MMA. MMA is matrix multiply accumulate. So it's very similar to the tiled kernel that we had before, where we're copying some data. Actually, we don't use shared memory here, so I shouldn't say it's similar to the tiled shared memory. It's actually very similar to the naive kernel that we have way before, like the very first kernel. So we're looping over the k dimension. We're copying some stuff from global memory into registers, and then we call this gem. And what this gem does is it actually translates into some hardware intrinsic, which does the actual matrix multiplication. So here's a very complicated diagram of how this works, how MMA works, how the tensor core works. So this core requires the MMA actually works on 32 threads. So MMA is a hardware atom. They call it hardware atom. It's like an instruction that you issue on 32 threads at the same time, and it will take registers in all the 32 threads that have data of the matrix in a very specific format in A and B, and then it'll compute C, doing this matrix multiplication here. So basically, the layout of the data has to be in a very specific format, like the thread zero, value zero. Has to be here for that matrix. Thread one has to have this value, and so on. T and V are thread and value here. If you have the data loaded in this very specific form, then you can issue that one instruction, which is going to be called. It has the dimensions here also. Like it'll have like 16x, 8x something, and then you can once that instruction is issued, it will actually do the matrix multiplication using the tensor cores. And the way we actually run this is like Qt has a facility, by the way, to print this. That I didn't generate this by hand. You can actually print it to a LaTeX, like all the thread formats. But if I just use a single tensor core instruction, it's not going to be sufficient to actually do this kernel. So I have a bigger tile size than the hardware atom. The hardware atom works on 16 by 8, but I have a much bigger, like I want to do a much bigger tile size in my kernel. So I'm actually tiling the hardware atom. So if you look at this slide, this uses more than 32 threads. Like this is just 32 threads. This is just showing one warp, like how the 32 threads are doing the MMA. But this time I'm actually using a lot more threads. You can see T47 and stuff. So I'm actually using uh, 32 times 4. So 128 threads. So 128 threads cooperatively. First, they load submatrix of A into their registers and the submatrix of B into their registers, and then they issue like 4 of these instructions, which is 4 atoms, and that will compute C in their registers. So this is kind of how it looks like. So this gem call actually translates into 32 hardware instructions, MMA instructions. And uh, basically, like the previous slide showed, like each warp, which is 32 threads, that does one atom. And this atom is tiled like this. On the top right of the slide shows the way those atoms are tiled. And then I'm also tiling. I'm within the same thread. That this is called spatial tiling, I think. And the tile below is uh, temporal, where basically the same thread is having more data because I want to fully utilize the registers of the thread. So this gem call, like I said, I do a copy and copy. Copy will move the data copy the data from global memory into the registers in a very specific combination. And then when you call gem in the hardware, it translates into 32 of those instructions. 32 instructions. Each one is computing a 16 by 8 result. So this one actually is using tensor cores, and when you compute the results are not numerically accurate anymore. And I'll show you that in a second if you have time. This one duration drops to like 25 milliseconds. We're now more than FP32 for cuBLAS because we're not numerically accurate anymore. It's not a fair comparison, but still we're only 13% of the TF32 cuBLAS code. So now we're going to explore more optimizations on top of this. So Qt, if you take away one thing from this presentation, I think try to use tensor cores, and I think Qt is a way to Qt is like a CUDA tensor library, and that's a easier way of using tensor cores as opposed to doing it by hand. So now I'm going to do a few more optimizations in 5 minutes that I have. The next one optimization is previously we were doing global memory to registers. Yeah.
Sorry, Ahmad. Just so you know, I understand it finishes in 5 minutes. If you need extra time, if you have the time, I'm more than happy to host it until you're done. Just so
Okay.
you know.
Yeah, I think
Sorry.
maybe I can do like maybe 15 minutes over. I don't know if folks are still interested or not.
But that's
Yeah.
fine. Take your time. It's better. We really appreciate this. I could tell you right now, this presentation is fantastic. So thank you.
So actually, if we do have the time, let me go to the VS Code stuff, and I'll show you what the code for this kind of looks like, right? So I'm here dumping the code. Actually, can everyone see it? Vincent, is the font too small?
It's a little small for me, at least.
Is it better now?
It's getting better, yeah. Maybe one extra notch in case. Yeah. If that works for you, then that works. That's really nice for me. Yes.
So this is the code for that cute simple. I mean, this is a C++ template code, so this is like the manual name of that function. But if you look at this, and I'll show you the code also. The code is here. It's called cute simple. So this, like I said, like I just call gem, which is like the function from cute, and this one translates into these HMMA instructions that you can see. Like this cute, and I'll actually show you the host code also. I think looking at the host code is also instructive. Uh, I think I should just make this a little bit bigger here. And so if you see the host code starts off with the MMA atom, and this atom says for SM80, I want to do TF32 TN. Ignore the last part here, but basically this is 16 by 8 by 8. So it's 16 by a matrix size 16 by 8 is being multiplied to a matrix that is 8 by 8, and the output is 16 by 8. And this is MNK like that. That's the host code. And when you look at this kernel code, you will see that it's doing a couple of copies. One is for matrix A, one is for submatrix B, and then you run the gem here. And the gem call translates into these HMMA instructions. This is if you were not using CUDA, you would have to run this, you would have to call this yourself as like an inline assembly. So this one, HMMA is the 1688 F32 TF32. This is the one that's actually doing telling the hardware to do the multiplication. And if you just grep HMAMA and you just do WC minus L, you'll find that it does 32 of these. So even though I'm calling gem once, because each thread has 32 copies, because of the way the atom is tiled for that bigger tile, like each thread is doing a much bigger tile, but the hardware instruction only does a small tile. So I have to have multiple copies of the hardware atom tiled in a very specific way for it to actually do 32 HMMAs. And I'll show you the results also. Like this is I'm running this on RunPod, which has an H100. If you look at this cute simple HMMA, you'll see the mismatches here. Like the GPU results is 4100.83, but the CPU result is 4101. So there's like a little bit of error here. But previously the results were all matching. Like I just sample 1000 elements in the C matrix, and I test them against the CPU to see like if the numerics are accurate or not. But let me go back to the slideshow. How do I do that?
Ahmad?
Yeah.
So there's two questions. So the first is from the Discord. They want to know how much does the Hopper hardware you use cost? And they want to know, does it just reside on your desktop or is it in a data center? And
Yeah, it is costly. I'm just like this run pod thing is I'm renting it for like $3 an hour or something like that for one hopper. But I think like my company has H100s that I use. But I think it's probably like I don't know, tens of thousands of dollars to get that.
okay. And so I guess you use it from and I guess their follow-up question was that your entire group use it, or does it do they come to you for your expertise?
Sorry, what was the question?
Sorry, so it's still related to the card. They want to know, does your entire group use the card, or do they come to you for this expertise?
I think like we share machines at Meta. So like there's one machine with eight H100s, and it's used by like machine learning researchers and people like me also, like systems people.
Okay, great. And so now the follow-up question for what you just presented here with all the what you were showing the number of HMMAs, I think it was called.
Yeah.
Yes. The was that were you using this CUDA object dump? Was that showing the assembly? So yes,
Yeah.
here.
Yeah, so the way I didn't go into those details, but basically, like the way compilation works is you write this code, NVCC compiles it down to a binary. You actually, if you look at the make file, you'll see that there's a CUDA arch here, this SM90. So each generation of NVIDIA hardware comes up has like a code like SM100, SM90 is Hopper, SM100 is Blackwell, and so on. So you pass it that arg, and the way it NVCC it compiles it into this intermediate language called PTX, which is hardware agnostic, and then it also compiles it down to the specific hardware that you ask. So the PTX is for backward compatibility or something. If you build a binary and if you run it on a different GPU, it'll JIT that into executable code, like the binary code for that particular GPU. But it also like because I know ahead of time that I'm running this on a Hopper, so I just pass in the SM90 flag, so it will actually include that in the FAT binary, the Hopper code, and if it knows that it's running on the Hopper, it'll just run that. Otherwise, it has to compute from PTX. PTX is virtual coded. I don't think it has register allocation at that point, and it has to do with like register allocation and running it on the code at runtime. It has to JIT that. I don't know if that does that answer the question?
I think so. So fundamentally, what you're showing here is the assembly for the actual architecture.
Yeah,
And
this one, like, because I did CU object dump minus SAS, SAS
yes.
is the actual assembly stuff. If I did dash PTX, it would actually show you the virtual ISA, but this is the actual ISA for SM90.
Okay, yeah, that was great. Thank you.
Okay. So let me go back to the slideshow. So like I said, the hardware atom does 16 by 8, and because we want to do bigger tiles, we have to tile it across warps. That means across threads, and also within the thread, you have to have multiple copies of this just so that you can perform this efficiently. And so that was the first kernel that was using tensor cores. Now we have to improve that to see like how far can we get, how close can we get to cuBLAS. So the next kernel is matmul qt smm, which basically like the previous kernel was just copying from global memory to registers and doing the MMA instruction on from those registers. But now we're just going to do tiling, which is similar to the earlier bandwidth saves that we did before. Now we're gonna asynchronously fetch from global memory to registers to try to bypass the L1 cache. And actually, sorry, it goes to shared memory and then to registers, and then you do MMA. And that one, like the code kind of looks like this. You do this copy to this shared memory, and then you copy from shared to, because this asynchronous copy, it doesn't support copying to registers directly. It has to copy from global memory to shared memory, and then from shared you copy it into registers. And again, like I'm just using copy from Qt library, but if you had to do this copy but manually, it would be a nightmare because you have to have this very specific format. Like threads have to have the values of the matrices in particular registers for the MMA instruction to work, for the tensor cores to work. So this is kind of what the code looks like for using Qt. And I'm showing you like a little bit of abridged code here because the full code may be a little bit longer. But the essence of the code is you do asynchronous copy from global to shared memory. You do like the way the hardware works is you have to mark that you've issued all the copies with this fence thing, and then you have to wait, and then you have to wait for this async wait here before sync threads only waits for your 32 threads to finish the loading, but you actually have to wait for all the threads to load, so that you have to have a sync threads also. And but when by this time when you have sync threads here, you are guaranteed that all the data is in shared memory. Then you copy from shared memory into your registers here, and then you do the gem. And again, the gem translates into like probably 32 HMMA instructions, which for each of them you do the sub-tile matrix multiplication, and then you sync threads again. So this one is like a template function based on how big of shared memory you have. Like I said, the more you have, the bigger your tile, the more you bandwidth you save because you're not you're doing less read amplification there from global to shared memory, and you can get 95 teraflops. So this is a little bit of a cheating because I'm comparing it to cuBLAS 32. So cuBLAS FP32, as a reminder, I told cuBLAS to keep the higher precision. So it's kind of running matrix multiplication on Hopper and telling it to have its hands tied behind its back. But now I should be comparing against TF32 because cuBLAS TF32 was doing the imprecise matrix multiplication, imprecise, like slightly lower precision math. So now we're getting about 30% of cuBLAS TF32, and we're getting 95 teraflops per second. But we can there's more room to go if I have a few more minutes. So the next thing to do is Hopper supports this thing called WGMMA. So Ampere, which was the previous generation of the SM, that supported MMA. And remember, just as a reminder, MMA was this matrix multiplication operation on 32 threads, which is one warp at a time. WGMMA is a grouped MMA. So four warps, which means 128 threads, they come together and they issue a matrix multiplication on much bigger tiles. So the reason why you need four warps is that you don't have like I feel like you can't have enough like registers for like a very big tile. And the other change that it did was it directly operates from SMEM. Remember the earlier code that I showed you? It was copying from global memory to shared memory to registers, and then doing the MMA synchronously from those registers. Hopper made this a lot simpler. So in Hopper, you copy from global memory to shared memory, and then you just issue one WGMMA, which directly reads the operands from shared memory. It's a much bigger tile. You don't have to copy to registers. And you can also do like later on, I'll show you how to improve the copy also. So this WGMMA is also better because it reduces the instruction issue pressure. In the previous code and even the SAS code that I showed you, we were doing 32 HMMAs, which was a bottleneck even for instruction issue. Here we just call one for four warps, we call one WGMMA, and it will load the data across like from shared memory on a much bigger tile and do the matrix multiplication there. And it's also async. This MMA instruction is async in the sense that you can issue this, and the hardware is going to read from the shared memory, do the matrix multiplication using the tensor core, and you can do the index math for the next loop iteration at the same time. So it's overlapping a little bit of compute, like index compute, like bookkeeping compute with the matrix multiplication. So now we're going from GMEM to SMEM to WGMMA, and the code kind of looks like this. It's a little bit more complicated code because now there's some race condition that you introduce because you're asking the tensor core to read from shared memory and accumulating into registers. The result is in registers. But you have to make sure you don't overwrite that shared memory while it's doing the compute here. So real quick, the performance for this one goes up to 168 teraflops, so 168 times 1e12, so 12 zeros multiplied by this. And now we're up to like 53% of cuBLAS, TF32, and we're like I said, this column is not fair, but we are 5 times more than the FP32 performance. And the last kernel is basically matmul with WGMMA, which is this grouped matrix multiplication asynchronous operation with TMA. So remember someone asked about what TMA is. TMA is this like tensor memory accelerator. It's a special hardware unit that you kind of program once and you tell it, hey, this is the format in global memory. This is how I want the format in shared memory. It will do the copy for you instead of you having to issue instructions for the copy. So before we were kind of issuing instructions and the SM like there was some more issue pressure, like there were more instructions that had to be executed. Here you just like one thread will actually issue the instruction for programming the copy. And this hardware unit is special in the sense that it also does bounds checking, so you don't have to do that much index math. So basically, it lowers the instruction issue pressure, it makes the code footprint probably also smaller. It does handle the hardware swizzling for you because the shared memory format has to be like a very particular format for the tensor cores to operate on it. It can also do multicasting, which is you can program the TMA to bring in a tile into two SMs as opposed to one SM. I haven't done that optimization, but I think probably cuBLAS does it. And now we're going to use hardware memory barriers instead of software, and we're also going to do pipelining. So what we will do is our pipeline is 3 stages. We will we are asking the TMA to bring in the memory from global memory into shared memory at one stage while we're doing the compute or the matrix FMAs in the other stage. So this is kind of how the kernel looks like. Again, I've kind of condensed it. The actual kernel code is on my GitHub if you're curious to look at the code. But here, this one gets us to it's template code based on the tile size. But if you use a tile size of 128 by 256, you can get to maybe 97% of TF32 cuBLAS. So cuBLAS does a few more tricks on top of this. And I can go into those, but I think that's probably I'm already over time. But I suspect cuBLAS does some like warp specialization and some other things on top to get to that performance. Harish had a question.
Hi, I could wait until the end. I mean, this is a very general question.
Yeah, so I think I'm also going to show you one more thing, which is like the NCU NVIDIA Compute Profiler tool, which is like it shows you all these kernels, like how many registers, like what's the duration. The last one is cuBLAS itself. The last two are actually cuBLAS. One of them is like FP32. The last one is TF32, and you can see like um, even like the cuBLAS kernel, if you look at line 8, row 18 here, it uses some weird grid size, 66 by 2. And the reason it does that is, again, that's like a micro optimization. You want, like, if there are 132 SMs, you don't want to have even that overhead of adding threads to the SM that can add overhead also. So you just that's called what is I think that's called a persistent kernel where you just launch as many blocks as there are SMs. So each SM just executes the same code again and again. It doesn't have to like clear out that block and allocate registers for the other block. So just to summarize, how do you get performance out of the H100? Try to use tensor cores. Try to keep the arithmetic hardware busy. Do more math work per warp if possible. Keep more warps in the system. That's the occupancy metrics that I showed you. Overlap compute and loads if possible. Use TMA for extra speed up. That's the last kernel that I showed you. And try to use Qt to keep the index math simple. Otherwise, like doing all of this stuff in your head is like it hurts your brain. And this is the repository. And if you have questions now, Harish, I'm gonna unmute you again for your question.
Yeah. Thank you for that talk. Really learned a lot. So, quick question. I'm assuming so the hardware and CUDA they have their own parallel evolution paths, right? And you've worked through multiple generations of hardware and multiple generations of CUDA. So knowing you talked about some of the intricacies of the hardware itself and how you have to code to the architecture. So when new generations of hardware, when they come and they become available, and you have written low-level infrastructure, right? Does it ever happen that it breaks your model in the sense that you've coded, let's say, to Ampere, and then Hopper came, and then there were certain things that you wrote, and it completely it performs worse now because it was written for Ampere and it doesn't go well with Hopper. And then when you go to Blackwell, you have to change some. Have you had that experience, or is that pretty smooth? Does hardware not break that performance backwards compatibility?
That's a good question. So I'll answer two. I'll give you two parts. One is functionality. Like I said, the way NVCC ecosystem works is you compile binary. When you compile the binary, you also compile it to PTX, and PTX gets converted into SAS, which is the streaming assembler converts that into the actual assembly code. So functionality wise, it doesn't break, and like CUDA is generally like
Mhm.
backwards compatible. For performance, I also think I haven't had a case where the performance regresses because generally speaking, they increase the sizes. They don't like decrease the sizes. Although maybe I think for FP64 they may have decreased the performance. I'm not 100% sure on that, but for generally speaking for like FP32 stuff, like I don't think I've seen a case where like the performance degrades because generally speaking the cache sizes increase from generation to generation, but trying to get the maximum performance for that generation because the new hardware unit is added, by default, it's not going to use it. Like by default, it will not use TMA, for example. And even like going from pre-Volta to Volta, Volta was the first one that had the tensor cores. You, without using like those special like MMA instructions, you were not able to fully utilize the tensor core or utilize them at all. So I think you need to like like for C++ code especially, you have to write those intrinsics. I think now NVIDIA has this language called Qtile, which is like higher level, like in Python. You can specify like closer to your algorithm, and it does the translation for you. So probably that is a better way to keep up with the latest architecture.
Great, thank you. Yeah, I assumed that it wouldn't break functionality or correctness. It was, and yeah, the sizes grow bigger. My concern was like the way something is unitized or uh, the partitioned. I thought I was wondering if there was like some kind of locality that was uh, broken or something like that. But it seems like you haven't seen any of that, so
Yeah,
that's
at
good.
least I
That's good
haven't
to know.
seen it. Yeah.
Yeah. All right. Thank you. Thanks a lot.
Yeah, my presentation is done. If there are no more questions, then I haven't checked Discord, but
Sure. No, so first of all, Ahmad, thank you so much. There is currently no questions on the Discord. Thank you for the extra time, Ahmad. I do have a question, and it's just related to what you were saying about the CUDA architecture being able to take the information from shared memory, do the computation without storing it in registers.
yeah,
Uh,
Hopper does that.
the Hopper does that. So fundamentally, what you're saying is that you give it the location in memory, it's able to retrieve the information, run it on some sort of functional unit, and then place it right back to memory without placing it into a register of the CPU.
I think
Sorry,
the
processor.
results were in registers. The results are in registers, but the input was in shared memory, as far as I remember.
Okay.
Yeah.
Okay. Well, that's a great feature to see. Um, okay. Give it a look. Okay. So it seems like there's no other questions on that. So thank you so much. We really appreciate this. So brief final remarks. Once again, next week there's going to be Mike. He's going to be presenting on 3 ways of writing an application: one by hand, one by AI, and then combined. There's also, once again, there's the user group, the Vienna user group, hosting something on Monday. Please go check that out. The Windsor C and C++ will be hosting a meeting in March, so please stay tuned for that. And once again, the NDC Toronto will be happening in May. Please look for your tickets. I think Jason Turner, like I mentioned, is giving a workshop. Lots of great presenters, and you get a discount code. Sorry, from the Discord if you're interested. Aside from that, I just want to encourage everybody to make sure that these events you're welcome to mention to all your friends and colleagues. And once again, Ahmad, thank you so much. It was a fantastic presentation,